Right. Let's continue. Any questions, any comments? Now I want to talk about identical particles. So far we almost had exclusively like single particle, but generally we can also deal with more than one particles in quantum mechanics. Like if you have, for example, two particles, we still write a wave function, but this wave function now is going to depend on two coordinates: the coordinate of the first particle, coordinate of the second particle, and also the time. And Schrödinger equation is also the same. So this is RH bar del psi del t is equal to h psi. And we also have normalization. So if you take this and if you square, that's the probability to have the first particle at R1 and the second particle at R2 at given time t. And if you integrate over all possible d cube R1 and d cube R2, you should get 1 because particles are somewhere for sure. And the Schrödinger equation in the Hamiltonian, in the Schrödinger equation, is the kinetic energy of the first particle minus h bar squared over 2m delta 1 squared minus h bar squared over 2m. It could also be m1 and m2. They don't have to have the same mass. So this is delta 2 squared. And there is some interaction. Maybe there is also external potential, but let me not write it. But they may have like something like so-called interaction potential between each other. I mean, this also may depend on time, but typically we don't have time dependence in here, right? So we generally have time independent potentials and time independent interactions. And now we can consider the cases. Let's consider two main cases. So case 1. So these particles may be non-interacting. So this is non-interacting system. In that case, this V can be written as a potential for the first particle. Let me call it like V1 of R1 plus potential for the second particle, V2 of R2. And we have to put a lot of indices, but other than that, there is almost no calculation, right? Because there are two particles, we have to keep track of particles and we have to put the indices. And in that case, the wave function is separable. This psi R1 and R2 can be written as a product of two wave functions. Let me call them like psi A R1 and psi B R2. And if we do exactly what we did for the separation of variables, I can also say total energy is energy of the first particle A plus energy of the second particle B. Right? I just plug this in the Schrödinger equation, which has this Hamiltonian. Now I separated the variables, and for each I have h bar squared over 2m del 1 squared psi A R1 plus V1 R1 psi A R1, and its energy is E A psi A R1, and the same for the second particle, right? So let me just copy and modify. I don't know, this is M1, M2, this is 2, this is B, this is 2, 2, to be and this is 2. And you solve each separately. And generally, if you remember, so this is going to have like a set of eigenvalues. This is going to have a set of eigenvalues, and each going to have like a solution. Let me call it n, and this is m. So this is n, this is m. And the total solution is just going to be a product. Psi, this R1, R2. Let me not write the vectors. They can be in any dimension, 1, 2, or 3 dimensions. And the solution is psi a n of R1 e to the minus I over h bar e a n t, and psi b m of R2 e to the minus I over h bar e b m times t. So this is a solution, and this shows the time depend. Okay, there's also time here. Time dependent Schrödinger equation. But we know any linear combination can also solve it, right? So this one, for example, is also a solution. Psi of R1, R2, t is equal to, let me call it like n and n prime. So this thing plus, and wherever I see n, I will put m prime, m prime, m prime, and m prime. So this is also a solution. If you have any doubts, you can plug this in and all derivatives cancel each other and satisfy Schrödinger equation. And any linear combination is going to be like this, like alpha and beta. And if these are properly normalized, what we are going to see is alpha squared plus beta squared is going to be 1. Because these two particles are going to be either on this state or on this state. So this is sometimes what we call product state. This is product state. And this is a terminology given by, I think, Schrödinger himself. This is entangled. So this is entangled in the sense, so these are like separate particles, right? I don't know. One is going this way, the other one is going that way. And this is R1, this is R2, and I can make a measurement on one of them, right? For example, I can measure R2, and as soon as I find M, right, EM for the energy of R2, I know immediately energy of R1 is EN, 100%. Or similarly, if I measure an energy on R2 and find EM prime, I know for sure energy of first particle is going to be N prime for sure. That's why they are called entangled. So at the moment, I'm not going to say anything about entanglement, but that's the definition. In the future, we may talk about it. So this was the first case. If particles do not interact, we can do all of these interesting things. Another interesting case is like if these particles interact with the central potential, which we consider actually this problem in the hydrogen atom. So this is case 2. So particles interact with central potential. In that case, we can do this coordinate transformation, right? We can define center of mass coordinates R1 M1 plus R2 M2 divided by R1 M1 plus M2, and this is the center of mass coordinate. We can also define relative coordinate R1 minus R2, and we plug in the Schrödinger equation, and because the potential is central potential, so this V R1 R2 only depends on magnitude of R1 minus R2. And in that case, we can reduce the two-body problem to one-body problem, like we talked before. But in the most general case, we cannot do any of these, right? Interactions are more, first particles are not non-interacting, they interact, and also interactions are not central. Like, let me give you an example to show you the complexity. We consider hydrogen, which is the simplest. Let's consider helium. Helium has one nucleus with plus 2e charge and 2 electrons in the orbit. And if you want to write the interaction, I will assume the nucleus is stationary in what we call like Born-Oppenheimer approximation. So this V of R1 and R2, I don't know, let me also give you a picture. So there's like some nucleus. So there's like something like R1, maybe another electron has like R2, and they have relative position R1 minus R2, and this interaction potential is going to depend. First, I have interaction with the nucleus, 1 over 4 pi epsilon naught, and this interaction is going to be like, there's like plus 2e here, minus e here, and minus e here. So this is going to be 2e squared over R1, the potential, minus 2e squared over R2, the Coulomb potential for the second electron, and also the interaction between these two electrons. And this is going to be plus, it's going to be repulsive, e squared over magnitude of R1 minus R2. Right? And this is a complex problem, you know, it cannot be solved analytically, but we have powerful approximation schemes that can describe this thing very well, which is the subject of second course. But now the point is, it can be very complex.
John, how do you show that problem is not central, potential is not central?
So because now this V R1 and R2 is not only a function of R1 minus R2, it also depends on R1 and R2 itself, right? So in the central potential, I need to have only this dependence and nothing else. Of course, it is central in some other sense, but that's not what we mean. Good. So this is the playground. Now I want to introduce what we call identical particles. And classically, when we look at particles, right, a ball going this way or a ball going that way, we can distinguish them. I mean, even if you don't want to forget, you can put like stamps, you can mark, and then there's like distinguishability in the classical world. And when I say like this wave function, psi R1, R2 is a product of two, what I mean is like first wave function is in the state psi A, R1, and the second wave function in the state psi B, R2. I can say that. But in the quantum world, I cannot say that, right? Because if this is an electron in A state and this is an electron in B state, there is no way I can distinguish which electron is on which state. That's why these two electrons have to share these states, right? So this is distinguishable. But in the quantum case, there's like indistinguishability, and there are like two ways to form indistinguishable wave functions, and it is like something like that. I have exactly the same state, but I also need to consider first electron being in the second state and second electron being in the first state. And there are two possible linear combinations, plus or 1 or minus 1. Okay, and this is psi A R2, and this is psi B R1. And if this psi A and psi B are normalized, and I assume psi A and psi B are not only normalized but also orthogonal wave functions, right? In that case, I also need this 1 over root 2 for proper normalization. And the thing about this wave function, that I can take this wave function, and it's like a one line of calculation. I can exchange R1 and R2. And if I exchange R1 and R2, the second term is going to be first term, and first term is going to be the second term. And at the end, I'm going to pick up a plus or minus this thing. So I can have either symmetric wave function or anti-symmetric wave function. So the symmetric wave function, this plus sign, we are going to call them bosons. Good. And anti-symmetric wave functions, we are going to call them fermions. Good. And there is something called spin statistic theorem in like relativistic quantum mechanics. If you are interested, you can learn the second part of this course, and you can learn a little bit more math. And maybe in a couple of years you can learn relativistic quantum mechanics, but what it says is like bosons are integer spin, okay, integer spin, and fermions are half integer. So this is what we call spin, and statistics means like this exchange. And spin and statistics theorem. So this is a theorem in relativistic quantum mechanics. It's a little bit more technical than this course. Good. And another interesting thing about this is like if you put A is equal to B and take minus sign, like fermions, you can immediately see that A is equal to B is psi A R1, psi A R2 minus psi A R2, psi A R1. Something minus itself is 0. We immediately see psi R1, psi R2 is equal to 0. That means two fermions cannot be in the same state. And that's a very important effect we will use repeatedly. This is called Pauli exclusion. Good. Any questions? And now the question is, are there any physical consequences of this symmetrization? And to convince you for that, I'm going to show you something called exchange force. So to simplify the discussion and write less things, let's consider 1D and two particles and two states, A and B. And I have three cases. One is distinguishable. In that case, psi x1 and x2 is A x1 plus times B x2. I can have bosons. In that case, this psi is exactly this plus this term with 1 and 2 replaced. This is 2, this is 1. And because I'm assuming these are normalized and orthonormal, right? Psi A and psi B are orthonormal. I'm just going to put root 2 here. And lastly, fermion case. And this is exactly the same thing, minus sign. And to see something observable, right, we need to calculate observables, see if they have any physical manifestations. I'm going to calculate expectation value of the difference between the particles. But because this can be plus or minus, I'm going to take square. In each state, let's calculate what this quantity is and see how this symmetrization requirement affects the result. If we see anything different in the symmetrized case, we know it is also fully quantum, because indistinguishability is a quantum phenomenon. Good, first case one. So distinguishable particles. So I'm going to write a lot of integrals, but we don't have to calculate anything. We just need to keep track of terms. I mean, if you want to write, let me know. I'll slow down because I can copy and paste. You may not be able to do that, but there is no calculation here. So let's first start with, right, this is what? This is expectation value of x1 squared in separately this state, or this state. Expectation value of x2 squared, similarly, minus 2 times expectation value of x1, x2. Right? So we need to calculate this. Okay, this is also inside. So we have plenty to calculate, but you'll see they are all almost all trivial. So let me start with x1 squared is equal to, I need to integrate over dx1 and dx2, and I need to have psi a x1 star, psi b x2 star. So that is the complex conjugate of this wave function. And I put x1 squared here, and the same thing without the complex conjugates. And you can see, so these two components, they don't do anything and they are normalized. This integral is just going to give 1. And one component, this one, and this one, x1 is just a label, right? It's just a label and it's integrated over. It is just the expectation value of position operator. So this is the position operator squared, and it's the expectation value in the state A. So this is psi A. Good. A lot of things that looks like needs to be calculated, but actually there's nothing. Right? Now I'll do the same thing for x2 squared, and because I calculated this, x1 and x2, they are like, right, just the same thing. In that case, I'm going to have expectation value of position operator in the B state. So this one is a little bit more work, but you'll see this is actually not. x1, x2 is equal to, I'll just copy the same thing. And I need to have x1, x2. And now I can separate this, right? Let's collect x1 terms, like this is dx1. So this is x1. So this is x1. And this is x1. And what remains is all dx2. Psi b star x2, this is x2, psi b x2. And now this is the expectation value of position operator in A, this is the expectation value of position operator in B, and I'm going to write it as x in A times x in B. Good. And at the end, so this x1 minus x2 squared in this distinguishable state is going to be equal to x squared A plus x squared B minus 2 x a x b. Good. Many things, but it looks a little bit more palatable. For identical particles, we will have to write more terms, and we just need to keep track of things. So let's do first. So the case 2, identical particles. Let's start with 1, and you'll see they're almost all, as long as you keep track of terms, they're almost all trivial. So because of this 1 over root 2 times 1 over root 2, I'm going to put 1 over 2 in front. So this is 1 over 2. So this is dx1, dx2, and this is psi a x1, psi b x2, plus or minus 1 and 2 exchanged. So 2, 1. So close this. And I'm calculating x1 squared. So this is x1 squared. And I'll take the complex conjugate just in a second. So this is complex conjugate, complex conjugate, complex, complex, and this is product. Good. There are like 2 terms here, 2 terms here. There will be in total 4 terms. So this is 1/2 dx1 dx2. So this is, I can take this term and let me also separate terms. So this can be like this term. And you can see I'm calculating x1 squared, so I'm also going to write x1 squared here. So this is x1 squared, and this is b, and b comes from here. So this is first term, x squared, first term. And so let me open a big parenthesis. I don't want to keep writing all of these things many times. I'll just copy and paste. And the second term, okay, I'll have 4 of these, and let's just write and see how we need to decorate. So this is first times first. This is first, right? So this is a x1 and plus or minus x1 squared b x1. So this will be b. And this is going to be b, I think this is still b x2, then nothing, and a x2. So this is a. So the indices goes like a, b, b, a, x1 squared. And if I do the same thing with this one, it's going to be again plus or minus, but it's going to go like b, a, b, and the last one is going to be b, b, so this is b, b, and a. Right, that makes sense, hopefully. A lot of terms, but you know, hopefully you don't have to write this on your page. So let me check. So this is a, b, b, a, b, b, a, b, b, a, b, b, a, and b, a, b, b, a, b, b, b. Okay, good. Now let's clear some mass. So b and a are orthonormal, right? When I integrate over x2, this is going to be 0. So I don't need to consider this middle term. And a and b are orthonormal. This is going to be 0. Nothing to consider here. So this one, like b, b, this is going to be 1. Nothing to consider. And this is going to be 1. Again, nothing to consider. And at the end, as you can see, I have expectation value of x squared in a and expectation value of x square in B, which is expectation value of x square, and there's 1/2, everything is going to cancel, and I'll have expectation value of x squared in A plus x squared in B, and I also need to have put this 1/2. A lot of terms, but if you didn't let your psychology down, it was actually a very easy calculation. Similarly, I can just calculate x2 squared, right? x2 squared is going to be, this requires no calculation because once you do it for 1, 2 comes for free because these are just symmetrically located labels. But x1, x2 is not like that, right? For x1, x2, I want to copy this. Let's copy the work we did and use. So now I want to calculate x1, x2. Now these are all going to be x1, and these are all going to be x2. So these are x2, 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 and x2. Good. And now let's write things one by one. So this is 1/2. So this is x in A and x in B plus or minus x operators in AB times in BA, right? This term, we can see this term is complex conjugate of this term. So what I'm going to do is I'm just going to square this. And similarly here, plus or minus xBA times xBA. So this is absolute value xAB squared, right? This is just this integral. And lastly, I have xB times xA. Good. And end of the calculation, right? The messy part is done. Now we can collect and compare what we found. So this thing is going to just, what we have is like x in A times, right, this one plus this one, and 1/2 is gone. X in B plus or minus 2 of these, and 1/2 x AB squared. Good. Now collect everything. So this x1 minus x2 squared in plus or minus in bosonic or fermionic case is going to be equal to, so what we found here is this plus this is xa plus xb, right? There are 2 of these. Let's copy. And this thing, let me just check. I lost a factor of 2 somewhere. Oh, I see. Yeah, this is because I need to calculate 2 times this, right? We are trying to calculate here 2 times, where did I write this? Okay, this 2 times expectation value of x1, x2. So I need to put that into. At the end, this becomes plus, actually minus 2x in A and x in B. So these are exactly, this is exactly the same as distinguishable particles, but we have this additional term. And this additional term comes with minus or plus. Okay, let me. Okay, it is here again, like there is one more minus I need to consider. So this minus, okay, where am I? Here. You can see there's like a minus here. Minus times plus or minus is minus or plus. This is going to be, so this minus times plus or minus became minus or plus, and what I have here is this x AB absolute value squared. Good? Okay, that's the end of the calculation. Now we can try to make sense of this. So this piece is exactly the same as distinguishable particles. Right? This is exactly what we found for distinguishable case here. Right? XA, XB minus 2 XA, XB. XA, XB minus 2 XA, XB. But there is like a new contribution. And this new contribution comes from indistinguishability or exchange symmetry. And the sign, right? So the sign is minus for boson. Plus case was for bosons, upper sign was for bosons, lower sign was for fermions. So for bosons, for plus bosons, we get a minus sign here, and that means the distance between the particles reduced, right? And decrease of delta x. Whereas for fermions, we have plus here, the distance between particles increased. So increase of delta x. Good. And because of this symmetry requirement, it looks as if these two particles repel each other if they are fermions, or they attract each other if they are bosons, right? Because that's the interpretation. If the distance between them is like forced to increase because of this symmetry requirement, we can interpret it as if a kind of force. And this force is repulsive or attractive depending on if you have bosons or fermions. And the name of this force is, I mean, it's not a force at all, right? It's like a geometric constraint on your system, but we call it exchange force. Good. And the important thing about this exchange force, right, there is this XAB, and if you look at what this XAB is, for example, let's take one of them. For example, this one. So this XAB is something like that. So this is X, X, and X. And there's like some this so this is x, this is the definition of xab, and when I look at this integral, what I see is like, I don't know, this is my 1D line. XA is like an orbital localized somewhere, right? This is psi A, and psi B is another orbital localized somewhere else, psi B. And for this integral to be non-zero, they need to have like an overlap. Right? If these two orbitals are like infinitely separated orbitals, there is no way this integral can give like a finite contribution. Right? That's why if like one electron is on Earth, another electron is on the moon, they are like so widely separated, their overlap is negligible. That's why for this kind of electrons, we don't need to consider indistinguishability. But if we are looking at two electrons in the orbit of a helium atom, right, they are within like a few angles from spacing, they are definitely going to have like overlap. Then we will have to consider exchange in that case. Good? Any questions? I have one last piece of things to complete the story, and then I'll call it a day. Sorry, I think, any questions? And yes? So this is 2, right? So this 2, These two or entire thing? Oh, this, yes, this one. This is 2. Yes, thank you. Yes, good job. Good to see somebody is checking my calculation. Let me check here. Yes, this is definitely 2. Okay, now like more background, no more calculation. Here's the information you need to know, and let me just summarize. So let's think about also total wave function, and total wave function also has spin, right? So we need to incorporate spin because spin is part of the degree of freedom. And if we have like a single particle, right, we have this orbital part. Orbital, we generally use orbital even for things that are not in the orbit. Orbital means some wave function. Unfortunately, that's the jargon. There's going to be like some orbital part, and there's also spin part of this wave function, right? For electron, there's like a position of electron in three-dimensional space, but also there's also a spin degree of freedom. And to fully specify the electron, I need to specify both of these. So this is one electron, and I also need to do it if I have 2 electrons. I need to have orbital part, R1 and R2 for each electron, and I need to have spin part, 1 and 2. But what I require from this total wave function is total anti-symmetry, right? If I am working with fermions, when I exchange these two, so this should be equal to minus if I exchange these two labels. And for this to happen, I have 2 options. I can either have symmetric spin part, and if the spin part is symmetric, for total anti-symmetry, orbital part should be anti-symmetric. If I have symmetric, if I have anti-symmetric spin part, to have the total anti-symmetry, orbital part should be the other way. Okay? So 2 cases. If chi 1, 2 is equal to chi 2, 1, and we know when this happens, if you have these triplets up, up, 1 over 2, up, down, minus down, up, plus, or you have down, down, so these triplets, right? Exchange any of 2 of them, you see nothing changes. That's why psi part, R1, R2, should be anti-symmetric, minus psi R2, R1. And if I have anti-symmetric spin part, like chi 1, 2 is equal to minus chi 2, 1, and this happens with the singlet, like we have seen yesterday. This is 1 over root 2, up, down, minus down, up. In that case, my orbital part has to be symmetric because spin already requires, does the symmetrization, so this is going to be plus. Good. And lastly, okay, sorry, I'll finish. If I have more than one particle, I just symmetrize the entire thing, right? So generally we have many, many electrons, and we can think about a cat with the labels 1, 2, dot, dot, dot. There's like some ith electron, dot, 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 some jth electron, and suppose I have n electrons, right? And if I do the exchange here, and this I and j incorporate everything, including spin. If I exchange this I and j, like j and I need to get plus for bosons, minus for electrons. And exchange is always done in pairwise, right? Any kind of permutation, I don't know if anybody showed you, any permutation can be expressed as a permutation of these binary operations. Okay? That's why considering this is enough. And this is going to separate our Hilbert space into 2, 1 for bosons, 1 for fermions. Good? Yes?
Can you explain again why we changed the places of J and I?
So because like I have like a bunch of electrons I'm looking, right? Of course this is like a classical picture, and I need to have indistinguishability. And in distinguishability it says I have I particle here and J particle here, and if I exchange these two, I need to have this symmetry requirement. And in my ket here, I need to have one slot for every single electron, and if I change the labels, I need to have this symmetry property. Exactly. So this thing we are doing is no different than this exchange we are doing for two electrons. And this is called generalized symmetrization principle. Good? All right, that's it. Thank you. Sorry.